Okay, ladies and gentlemen, hey, welcome to this webinar, which is called What is Reliability? So just a couple of admin points. You can see I'm being very relaxed today with my t-shirt, but also I'm sporting an injury where I had to have surgery last week after coming off a mountain bike. The surgeon had to remove half of a forest, which somehow got embedded in my arm. And apparently the medical experts say that's not a good thing. And so there's a chance, because I tend to move my hands around a lot, there's a chance that I'll just do something with the stitches and I might have a sharp stabbing pain, which might come through in my facial expression. I'll work through it, but I'll just give you a heads up that's going to happen potentially today. So welcome to this webinar, What is Reliability? It's actually one of the most important things we do as reliability engineers, obviously, and quality engineers and designers and manufacturers, is to understand what reliability is. Problem with reliability, though, is that it's a phrase that we have all used since early school. I'm not sure when we first started becoming aware of the word reliability, but let's just say 5 years old, 6 years old, 7 years old. And the problem with that is that the concept of reliability is embedded into our vocabulary before we actually go off to universities or go to the real world and understand what reliability actually is. And the number of times we steam past this definition of reliability before we start talking about it is astounding. And so many things can be done, or so much money can be saved, so much time wasting can be averted if we just understand what reliability is from the very start. And that's what this webinar is about today. It's all about what is reliability. And again, we all have these preconceived ideas of what something like this ball bearing is, or the reliability of something like this ball bearing when it comes to reliability. Now, this ball bearing is just like any other product component device there is. It will eventually fail. And when it does, it's going to be failing through a random process, because failure is a random process. So this ball bearing is not going to be failing at a specific point in time that we can predict years, months, days in advance with absolute certainty. And so what that essentially means is that when it comes to understanding what reliability is, this needs my computer to catch up with the animation. It essentially means that seemingly identical machines or components or systems like ball bearings will fail at frustratingly different times. And we, as reliability engineers, need to not only come to terms with this, but embrace this. So why do seemingly identical ball bearings fail at different times? Well, these seemingly identical ball bearings aren't actually identical. They're indistinguishable to us. These might be from the same manufacturer in the same batch, but we know that if we were to zoom in, so to speak, on one ball bearing versus the other, the one on the left, it might have an impurity right there in its inner race, while the other ball bearing on the right might have a dislocation in its atomic lattice. And these things matter. Every single ball bearing will have defects and flaws. Even the highest quality ball bearings will not have inner and outer races and steel balls with perfect atomic crystals throughout the entirety of the alloy. It's just a fact of life. And essentially, these impurities, these imperfections that we cannot truly eliminate become the triggers for failure later on. And because even though the physics teaches us that if we were to hypothetically know the location of every single atom and understand with precise knowledge the stresses each atom was going to experience in the service life of this ball bearing, then theoretically we'll be able to predict exactly when it fails in a very deterministic way. The level of knowledge we need to be able to do that is beyond the computational skills of any device we know. So for all intents and purposes, we cannot characterize how our ball bearings will work and fail with this level of understanding, and therefore we have uncertainty. And every time we have uncertainty, we have a random process. And so reliability engineers, designers need to embrace this reality. If we pretend this is not real, even though our human brains don't like this, we don't design reliable stuff because we don't embrace reliability. Much like my computer is right now. It's supposed to be moving on. Excuse me. Now, this might seem as a problem, and in some certain perspectives, it is. The inability to not understand exactly how things will fail is a problem. Now, the way many veterans to my webinars will be familiar with this, but the way I illustrate this random process of failure is with this random hand of failure, and this represents all the uncertainties, all the different factors that we cannot possibly comprehend that will drive the failure of one ball bearing to occur slightly earlier than the failure of another. And so seemingly identical ball bearings, and when we say seemingly identical, the word we should be using is indistinguishable to us, will fail at different times, even when they are used in seemingly identical situations. And so beneath our random hand of failure, we add this line here, which represents the time to failure of our ball bearing. Now, of course, we don't, time is a term that we use a lot in reliability, but in practice, it's more aligned with the concept of age. So for our ball bearing, time is measured in cycles or revolutions, I should say. How old is your ball bearing? It's not necessarily how long it's been since it was manufactured. The age of a ball bearing comes down to how many times that inner race rotates with respect to the outer race, along with all the stresses associated with that. So time in this concept, in this scenario, represents number of cycles or revolutions our ball bearing experiences. And this is the same for every single product out there. The age of something is not just measured in terms of time, but to make things simple, we use the acronym TTF, T standing first, the first T standing representing time, to represent the age of something, how old something is. So the random hand of failure, which characterizes the uncertainties, includes, for ball bearings, particle contamination, misalignment, disassembly damage, insufficient lubrication, humidity, which then triggers corrosion, excessive loads, and manufacturing defects. Now we have all these different factors influencing how long it will take for seemingly identical ball bearings to fail. And those little slices represent the respective contributions to ball bearing failure. You can see the biggest contributor is particle contamination. And one of the smallest contributors is manufacturing defects. And that's because we know how to manufacture highly reliable ball bearings. It comes down to more or less comes down to how we treat our ball bearings in the real world. Sometimes we cannot avoid particles contaminating our ball bearings, but there's plenty of scenarios where we can. Nonetheless, as a rule, we have these different factors influencing how long seemingly identical ball bearings will last before they fail. And that means that if we're to observe, in this case, 100 ball bearings until they failed, with each one of these blue data points you can see on the screen representing the time to failure of one of those ball bearings, we have that spread, we have that uncertainty. Now, just because something is random doesn't mean it's not predictable. So time to failure, this is the outcome of this random process that is failure. It can, all those different practical issues or factors will be brought to bear in terms of the influence on the time to failure of that product. But like I said, just because something is random doesn't mean it is unpredictable. Now, random means there is uncertainty involved. A lot of people hear the word random and go, oh, so we have no idea about when something's going to happen. Far from it. We know that, for example, there's a 50% chance that if we toss a coin, we'll have a head versus a tail. That's knowledge. We know that when we roll a dice, there's a 1 in 6 chance that we'll see the number 6 roll. And the same thing applies to reliability. Even though something is random, if we study it well enough or are able to analyze it, we should have a really good idea of the nature of that random process. So just because something is random doesn't mean it's not predictable. Think of the height of human beings. So I'm 6'3", and the height of every other human being is the result of a random process, which involves genetics, diet, exercise, you name it. And we know that as a rule, human beings tend to range from a height of about 5 foot at the lower end of the scale, maybe a bit lower, to almost up to 7 foot at the higher end of the scale. And of course, there's a few outliers. So straight away, we know most human beings are between 5 and 7 feet tall. Still our height is a random variable. So we know there's no 10-foot human beings out there. So we can make some prediction about how tall we are, or how tall a randomly selected human being will be. It's random, but we still have a pretty good idea of the typical heights we'd expect. In fact, if we were to go to certain countries, we would be able to do a bit of research and say with a fair amount of certainty what the typical height of a randomly selected male or female human being would be. So just because something is random doesn't mean it's not predictable. Now let's try and apply this to our ball bearing. We can see straight away there is a pattern emerging. There's a data point density is higher in that region I've just circled. And the data point density outside that circled region or a ringed region is a lot lower. And that just simply means that straight away, our ball bearings are more likely to fail within that region, that time to failure region. Hopefully you're with me so far. So we can see a pattern emerging straight away. But it's not really easy to see that pattern or the density with these data points. We can see that region has a higher density of data points, but it's not easy to see how dense those data points are. Enter the histogram. The histogram is a much better visual representation method of the density of data points, including random data points. And you can see that's there's a clear shape starting to emerge in this histogram of 100 times to failure, or 100 ball bearing times to failure. It's not perfectly smooth, it's a bit jaggedy, but we can start to see there's a lot more information in this shape than that simple circle I drew around that region of more dense, of more tightly packed data points. And so if we were to keep going, because we're not really, let's just say we're not happy with how smooth this histogram is. And some people might be able to say, well, I can draw a line of best fit through that histogram and sort of come up with a curve that sort of resembles many other curves I've seen in the world of reliability that characterizes the random failure process. Others of us might say, you know what, I need to have more certainty about what the shape of this curve is. And so to try and do that, we can just essentially get a lot more information. Certainty is here. It comes when we have more information about a process. So one way to get more information is to test an incredible number of ball bearings, see their times to failure. When we do, the histogram will collapse to a beautifully smooth curve like this. This is what the histogram would look like if we had an inconceivably huge amount of information / data. Perhaps this curve here should be called the ultimate histogram. Now, for those of you who've done statistics in the past, you might know what the name of this curve is. But before we go to that name, what this curve does is it illustrates the likelihood of our ball bearing failing at a particular point in time. The higher the curve, the more likely it is for that ball bearing to fail where that curve is the highest. And as the curve gets lower and lower and lower, it represents a decreasing likelihood for our ball bearing to fail at that particular point in time. So we can see it's very unlikely for our ball bearing to fail when it's very, very young. And it's also very unlikely for our ball bearing to be able to be old enough to fail to the right-hand side of this curve. So the majority of ball bearings are going to fail around the region where that curve is the highest. Now, this curve, the boring, statistically mathy name for this curve is the probability density curve. And this probability density curve characterizes a random process. It tells us everything we possibly know about where this random variable will fall on the horizontal axis, or the value of that random variable. So this is, in a way, the holy grail of reliability data analysis. We want to understand this curve for our ball bearings, for our smart locks, for our bicycles, or whatever it is we are studying and trying to understand. And I can see there's a comment coming through. Is there a workbook for this session? Sahil, if you look at the comments box where you wrote that comment, scroll up ever so slightly, you'll find the answer to that question. Okay, so if we keep going and we look at this probability density curve from a more analytical perspective, how can we use this curve right here to be able to learn something about the reliability of our products? Well, I start using the term reliability. How do we turn this into reliability? Some people think this is reliability. It's not. It contains all the information we need to understand reliability. But how do we get to this concept of reliability? Well, this curve has a corresponding reliability curve. And you can see this blue curve, this starts high and then it decreases over time. This reliability curve starting high and decreasing over time. And you know what? It contains exactly the same information as that red probability density curve. So we're starting to get a bit closer towards reliability, but how do we do it? How do we get a reliability curve from a probability density curve? And what's the difference between the two of them? So what is this lunatic from Australia based in Canada talking about when it comes to these two curves here? Hopefully you're with me with that red probability density curve so far, but maybe this blue curve is a bridge too far. And if it is, don't worry, we'll get there. So if we go back to our probability density curve and just have a small cameo from our random hand of failure just to get those 100 data points back. And you can see that these 100 data points, which represent the times to failure of 100 ball bearings, you can see they're more tightly clustered around the region where that probability density curve is the highest. It's exactly what the probability density curve does. Tells us where, or with what likelihood, we would expect to see data points fall along that horizontal axis. So essentially, the density of those data points corresponds with the height of that probability density curve. Now, another way of looking at this data is by, instead of looking at the density, plotting this data on a chart where the vertical axis is the percentage of things that haven't failed. And now we have a different curve. The curve is no longer a line on the horizontal axis. We have these data points creating a much smoother line that starts at 100% and tends to go down all the way to 0%, because the vertical axis is now we define it to be the percentage of things that haven't failed. Our data hasn't changed. It's just being visually represented in a different way. Now, if we were to get an incredible number of data points, that line would smooth out to create a beautifully smooth curve. You might have sneakily noticed on the left-hand side, the title of that vertical axis is no longer percentage of things that haven't failed. It is now reliability. This is the reliability curve for that ball bearing. It starts off at 100% and goes down to 0. All that means is that everything will eventually fail. At the start, everything's working, and eventually, as things get old enough, they will stop working. This is not groundbreaking. This is the reliability curve for our ball bearing, and it's based on exactly the same information that gave us our probability density curve. And so our reliability curve can also tell us, for example, if we have what's called dead on arrival failures. On the left-hand side, you can see that our reliability curve now starts at 85%. And so this reliability curve now gives information about different ways things fail. The dead on arrival failure is on the left. What's a dead on arrival failure or out of the box failure? It means that this product whose reliability curve this is, 15% of them never worked for our customers, users, or clients when they came out of the box. Now, reliability curve will characterize or capture that based on where it starts on the vertical axis. So as a rule, there is a chance some products won't work when they come out of the box. There's always that chance. But in many cases, that probability is so low that most reliability curves tend to start at 100% or there or close enough. For example, ball bearings are pretty robust. They're very unlikely to fail during transit from the factory from which we got them. And as a rule, most of them, or almost all of them, should be working out of the box. So the reliability curve for this ball bearing is going to start at 100%. Okay, and what can we learn from this reliability curve? Well, if we move down our reliability curve, so let's just watch this animation as we have our little cursor, so to speak, move down our reliability curve until the reliability curve is exactly 50% high. You might have noticed that when we did this, all those data points and the first part of the highest part of the reliability curve fell away. Well, we know that because we've gone 50% of the way down that curve, exactly half of all data points have fallen out. So we only have half of our ball bearings remaining, or 50%. This point in time, or the time where their reliability curve hits 50%, is also known as the B50 life, or at least for ball bearings it is, where we have a 50% failure probability or 50% reliability. Now, that is also known as the median life. And you can see that this is pretty useful information, and reliability will always eventually decrease to zero as it moves to the left. Now, the B50 life is also, we see that a lot in the world of bearing reliability. Now, the B50 life is such a useful concept that other industries started using it after the bearing industry came up with the B50 life. But instead of using the letter B, because B stands for bearing, you'll often see the L50 life. And essentially, the L50 life is the median life, the time by which we expect half of all things to have failed when they are not ball bearings. So L50 refers to that median life for things that aren't ball bearings, and B50 refers to the median life for things that are ball bearings. And like I said, as the reliability curve eventually decreases to zero, what that means is that eventually everything fails. It's just the way it is. Now, we might be fascinated by this curve, or maybe unduly fascinated by this curve in the world of reliability engineering because, well, it's such a useful concept, one would think. But as a rule, we aren't interested in most of this curve. Whereas not interested in the trivial thousands or the last 90% of failures. For example, ball bearings, we want to replace those ball bearings before they fail. They wear out. We can often have lots of different sensors and different things in the manufacturing facilities that have ball bearings, or otherwise put ball bearings into automotive applications where they should never fail or have a very low probability of failing during the useful life of a vehicle. So as a rule, we aren't interested in this part of the reliability curve. When more than 5-10% of ball bearings have failed, you have a problem. That will either mean that your plant is shutting down way too often to replace ball bearings that have failed, or your vehicles simply just don't work anymore and your brand is trashed. And when it comes to the reliability or perceived reliability of your automobile. So we're always interested, as a rule, in the first part of our reliability curve, because our system stops being useful after a small fraction have failed. And that's something we need to really wrap our heads around. We aren't interested in the trivial thousands of things that will fail after the first 3, 5, 10% of things have failed. If you're in the business of warranty reliability, you go out of business if you have more than 5 to 10% of your things failing during the warranty period. So that first part of the reliability curve is the most important part, which is actually very useful because that's the easiest part of the curve to get data on. The time to failure of the last few survivors, that's a lot harder to analyze and test for and predict. And you know what? We don't need to. It's all about those first early failures. So that's our reliability curve for our ball bearing in a nutshell. So another little key metric or key statistic that we can use, we look at the B50 life for our ball bearing, but now we can look at this other thing called the B10 life. And if you are able to follow me with the B50 life concept, well, the B10 life is the time by which we expect 10% of ball bearings to have failed. And a lot of manufacturers will advertise their B10 life. This gives you some indication about when your ball bearings are going to stop being useful, so to speak. Their probability of failure becomes too high for even the most loose business cases that exist out in the real world. The B10 life is the time by which 10% of things have failed, or in other words, the time at which the reliability of our ball bearing has dropped to 90%. So hopefully just with this sort of random discussion about this curve and B10 and B50 lives, you are starting to come to starting to really understand and become comfortable with the concept of this reliability curve. That's the plan at mine anyway. Yeshwant asks, are regression models a valid technique to predict reliability? What would be a drawback by using them? Now, great question, but that's outside the scope of this webinar as of right now, as in this webinar is all about what is reliability. So Yeshwant, I'll come back to you at the end if we have time. So here's our reliability curve, those data points gone. And now we're going to compare our reliability curve, that probability density curve for our ball bearing, which we talked about earlier. Like I said, these two curves contain exactly the same information for a particular product. But as you can see, visually, they're very, very different. So what does that mean? Well, it means that one curve defines the other. So if we know the probability density curve for a ball bearing, we can use it to draw our reliability curve and vice versa. So how do we do that? How are these two curves actually related in practice? Well, the way to look at this is that the reliability curve is the right side area under the probability density curve. Now, they're just words, and they probably don't mean a lot. However, just remember the concept of the right side area under the probability density curve and watch the screen. We're going to move from left to right. We're going to trace out our reliability curve as we draw this right side area thing under our probability density curve. So just watch this as we trace out first part of our reliability curve. You guys see that? See how we traced out the reliability curve as we move from left to right, and you can see that right side area under our probability density curve all the way down to 90% reliability. So that right side area takes up 90% of the space under the probability density curve. And we can see that this occurs at exactly the same time because it has to. They both describe the same random failure process, i.e. the process of that ball bearing on the right. And so because each one contains exactly the same amount of information, all we're doing is looking at that information from different lenses. The probability density curve at the top is all about areas, and the reliability curve at the bottom is all about values. Now, the probability density curve aligns with how our brains like to characterize uncertainty. We like to see curves. The higher the curve, the more likely something is. But then when it comes to doing the engineering stuff, we actually need to get the area under that curve to try and put numbers in documents and predictions and analyses and the rest. However, that's hard to do. And that's where the reliability curve comes into play. If we can get the reliability curve, essentially the reliability curve has done all the hard work of trying to characterize the area under our probability density curve. And so both these curves, for example, allow us to work out where that B10 life is for our ball bearing. Exactly the same points based on the definition of what a B10 life is. And if we keep tracing from left to right down to the B50 the B50 life, you can see, well, the reliability curve is exactly 50%, and the right side area under our probability density curve is also exactly 50%. So both curves contain exactly the same information for our ball bearing. So hopefully you can see how these two curves interact or relate, or how one curve allows us to draw the other and vice versa. So we want to have both curves in our sort of vocabulary of random stuff, but we need to understand why they're very different. So the reliability curve, remember, what is reliability? That's the concept, or that's the title of today's webinar. Well, that's reliability right there. It's a curve. It changes over time. And so we need to dig a little bit deeper into understanding what reliability is for your product. Because often when someone says, what's the reliability of something, they're not interested in seeing a curve like that. They're more interested in hearing a number which helps them make decisions. So what does that mean? It means that we need to define reliability. Reliability is the probability that an item will not fail for a designated period under specified conditions. So this is what reliability is. And we need to relate that to the curve. And the reason why we need to relate that to the curve is because there's 4 parts to the definition of reliability. The first thing is the definition of failure. You might be surprised. We often don't do that very well. For example, does failure occur when the piston is corroded but still works, or when the piston has seized? Now, you might swap out the piston if it's corroded when you inspect it, but it's still working. So what is failure? What is time to failure? What does failure mean for your device? Get that right from the very, very start. That's the first part of the definition of reliability. What is a failure? Second part is the specified conditions. So our ball bearing works great in a factory setting because that's what it was designed to do. But if you take that ball bearing to an unprotected mine site in tropical country somewhere across the world where the temperature is very high, humidity is also very high, lots of contaminants, well, it's not going to last nearly as long. And that's not the ball bearing's fault. So that's the second part of the definition of reliability. The third part is designated period. And that's where the curve part comes into play, because you need to define how long you're interested in understanding reliability for to get that number from the curve. You need to work out how far along the curve you need to go to get your number. So the designated period, is it 1 year? Is it a 2-year warranty period? Is it a 10-year service life? Is it a 6-month early failure frustration period for your client? Each different period will have a different reliability value and therefore should have a different reliability target. And last but not least is that reliability is a probability. And this infuriates us the most. Most of the people who are listening to me talk are technically minded people. And what that means is we like it when 1 + 1 = 2. We don't like it when 1 + 1 is equal to roughly 2, but not exactly 2. So why is this word probability very important? Because we have to use it when we're talking about a characteristic for a random process. When it's a random process, you deal with probabilities, unfortunately. 1 + 1 does not always equal 2 if that addition process is random. And we don't like that, but we need to come to terms with that. So that's a definition of reliability. Now, the probability density curve, which we just looked at, which allows us to get this concept of reliability, is also a very useful way of looking at another important metric in the world of reliability engineering. So what I'm going to do right now is I'm going to turn this curve into a shape and balance this shape perfectly. So, question for any one of you guys. What do we call that balance point? And I know some veterans from my webinars will know what it is, but let's just run through this process of getting attendee engagement. What is that balance point? What's that balance point called? The mean. Fantastic. It's the mean. That's all the mean of something is. It's the balance point of our probability density curve. You might look in textbooks and find equations and everything else. All those equations do is tell you where the balance point is. So why do we choose the balance point for perhaps the most widely used term in reliability engineering, at the very least statistics? Well, statisticians and mathematicians have constantly struggled to try and find a way of characterizing a typical value of a random process or a random variable. And so there's a bunch of things called the measures of central tendency. The mean is one of them. The B50 life is another one. B50 life is not the mean. The B50 life is not the balance point. So there's lots of things called the mean, the median, the mode, geometric mean, which are all different ways of statisticians have come up with to characterize a sort of central or typical value of a random variable. And the mean just happens to be the balance point version, which for a few reasons has become the preferred way of characterizing the typical value of a random variable. And we often use the letter or Greek lowercase letter mu to represent the mean. Or in reliability engineering, you might have heard the MTTF, the mean time to failure, or if your system's repairable, if you're going to replace your ball bearing every time it fails, the mean time between failure. Simply the balance point of the times to failure or the times between failure. And there's nothing more significant than that. It doesn't have a physical meaning. It doesn't have something you can see or walk past and say, that's the mean. That's all the mean is, the balance point of the probability density curve, or if you had a million, billion, trillion data points, the balance point of those million, trillion, billion data points. That's all the mean is. Nothing more profound than that. But unfortunately, we tend to worship the mean in a very unhelpful way. So here's our probability density curve with the mean for our ball bearing. Now, what we're going to do is pay close attention to what's about to happen, is we're going to look at different shaped probability density curves from the world of reliability engineering, where the mean doesn't change. So everything you're about to see is a bunch of different curves where they all have precisely the same balance point. So this is what it looks like for the ball bearing. And this is what it looks like for another device. You can see we now have this orange curve vertically hugging the vertical axis. This might seem very antithetical or a very uncomfortable way of visualizing a random process, including time to failure. In fact, you might think this is just a randomly drawn line on a chart, just to illustrate how the mean can be a very weird thing. Now, this orange curve, which hugs the vertical and horizontal axes, the balance point is exactly where it is shown on the screen, even though we can clearly see that most of the curve is to the left of the mean. And that's because the curve to the right of the mean extends so far to the right that effectively counterbalances the majority of the area on the left. Now, this is the probability density curve of the time to failure of something like a small satellite. Now, a small satellite is a device or a product that we know very well. And when I say small satellite, I'm talking about a really small satellite. Now, small satellites fail in a very different way to ball bearings. This is the probability density curve of a small satellite. The mean time to failure hasn't changed one little bit. But you can see there's a whole different characteristic of failure involved in this product. The mean hasn't changed, the balance point hasn't changed, the shape of that curve has. And that means that if we were to get a random hand of failure for our small satellite, most of the data points would be clustered to the far end of our, or the far left of our time to failure curve. The reason why is because small satellites fail almost exclusively to what we call wear-in or infant mortality. And that means that a fraction of our products carry problems that cause early failures. Now, small satellites are somewhat unique in that multiple studies have shown that virtually every failure a small satellite experiences is down to infant mortality, where there's some sort of pre-existing problem that causes that failure. But when you scratch the surface, it actually makes sense. Small satellites are very sensitive products. They are exposed to all sorts of stresses when they go through the launch process. None of the components are designed to be in space. Well, not none. Most of the components aren't designed to be in space. Most of the components are components designed to be working in mobile phones or computers and not space applications. The size of the market for small satellite doesn't demand electronic component manufacturers to create space-specific capacitors and resistors anymore. And so a lot of the parts are sort of repurposed from different applications. And you often have small satellite manufacturers make very small batches of small satellites with maybe months between production runs. So that's very hard to have continual improvement the way Toyota can, for example, in their mass production system. Now, what that means, though, from a reliability perspective, is essentially a little bit counterintuitive. Those that still work appear to be more reliable. That is, the older a small satellite is, the less likely it is to have defects causing failure, which means that that older small satellite is actually going to last a lot longer in a probabilistic sense than a brand new small satellite. So the reliability isn't changing. It's just that in a way, you're weeding out or screening out those which have the biggest defects, the biggest problems. And so we have this very different reliability characteristic. We don't talk a lot about this, though, in the world of reliability. Most products will have some elements of infant mortality or wear in. Maybe 5% of your products will fail with this probability density curve in mind, and the rest will then happily get through that early challenge and then move on to slowly wearing out the way a ball bearing does. So wearing or infant mortality is caused by things like manufacturing defects, assembly or installation error, interface issues, software bugs, damage during transit or launch, and any other way you can think of that a brand new product will have some imperfection or some deviation from what would ideally be out there for your product. So this is what failure looks like for our small satellite. The mean time to failure, like I said, I'm harping on this, has not changed when compared to that ball bearing. And like I said, it's because the curve extends so far to the right, those small number of data points, the small amount of area under the curve essentially perfectly counterbalances the large area to the left. And when I say large area, I mean 80% of the area. That means that about 80% of small satellites will fail by the mean time to failure. Just remember that 80% of things will fail, 80% of things that fail exclusively due to wear in or infant mortality will have failed by the mean time to failure. Now, this number decreases drastically for our ball bearing, but it's still relatively high. 54% of the total area under the probability density curve for the time to failure of our ball bearing is to the left of the mean, which means 54% of ball bearings will fail by the mean time to failure. And there's a reason why this number is very different, because failure is very different. Now, here's a different curve, which is perfectly balanced on that mean time to failure. And you might know this shape has a particular name. This is called the bell curve. And the reason why it's called the bell curve is because it looks like a bell. So you can see in this case, when we have our probability density curve perfectly balanced on our mean time to failure, exactly half of the area is to the left of that balance point. This only happens when the curve is symmetrical. Now, this is the probability density curve of the time to failure of things like tires, where they wear out in a very uniform way. That is, for every mile or kilometer you drive on a tire, you lose around about the same amount of tread. And so when that wear adds up in a very uniform way, you always get the bell curve. So we know how things fail, and everything has a characteristic probability density curve, or every failure mechanism, I should say, has a characteristic probability density curve that contains a lot of useful information. But you can see that no matter what we do, you will expect anywhere between 80% to 50% of your things failing by the mean time to failure of something. Now, the tire and the ball bearing are failing in a different way because they're accumulating damage. As opposed to an older small satellite being appearing to be more reliable. Well, the older the tire or the older the ball bearing, the more damage it has accumulated, so it's less robust. Now, when you do have the probability density curve of something which is accumulating damage, and you can plot it out like this, and you see a peak at the top, regardless of the shape of that peak. So there's a probability density curve for our ball bearings. You can see there's two mountains, two hills, two maxima, whatever you want to call it. That is the signature of wear out. So every time you see PDF curves which have a peak, you know without having to do any root cause analysis that your product is failing because it accumulates damage up until a critical point where it fails, what we call wear out. All that means is that things that wear out tend to fail around some central value somewhere. So what's wear out? Wear out involves failure mechanisms like fatigue, where cracks grow slowly over time, oxidation, when material reacts with oxygen. Corrosion is a special type of oxidation, where the oxidation is occurring with a metal. And essentially, that wonderful alloy we took a lot of time and effort to refine and have that beautiful eutectic alloy composition, not competition. Well, over time, corrosion screws that up and makes our product weaker. So the older your alloy gets, the weaker or more damage it becomes due to corrosion. Creep, where solid things slowly deform over time when they're being exposed to stress, which is exactly what happens when glaciers move in the Arctic and Antarctic and Himalayas. Where stuff is abraded away, which happens a lot, including for our tires. Lubricant contamination, where particles get into our lubricant, meaning the lubricant doesn't do nearly as good a job as it gets older. That's why we continually replace lubricants. Diffusion, where atoms move during through the silicon crystals of electronic components. And so here are a few examples of things that wear out. By the way, brief touch on maintenance. The only failure mechanisms that you should ever do preventive or predictive maintenance on are things that wear out by definition. If you touch something which fails due to infant mortality, by definition, you're only going to make it worse. Preventive maintenance and predictive maintenance and condition-based monitoring is all about addressing the accumulation of damage. So if you don't see a probability density curve with a peak, don't do preventive, predictive maintenance or condition-based maintenance. You are wasting your time and money and making things worse. Okay, so let's look at our tire probability density curve, but through a different lens. We're going to look at the time by which we expect 10% of our tires to have failed by finding the time by which we have 10% of the area under our probability density curve remaining. Like I said, that's the L10 life. It's not the B10 life because it's not a bearing. That's the L10 life, time by which we expect 10% of our tires to have failed. Now let's compare this L10 life, again, with the same mean, to the probability density curve from the ball bearing. You might have noticed that the L10 life of our ball bearing, which is also the B10 life, it moved a little bit. And for those who didn't see it, let's just compare the two probability density curves. You can see that even though the bell curve and our ball bearing probability density curve have exactly the same balance point, i.e. mean, well, the L10 life is quite different. It might look like a little difference on the left-hand side, but if you actually zoom in, we're talking about a huge change in terms of the magnitude of the L10 life. And when we compare this L10 life to the L10 life of our small satellite, then things get really freaky, because it might seem crazy, but our L10 life for our small satellite is extraordinarily close to zero because it's failing exclusively due from infant mortality. We have a huge number of failures really early. And so the L10 life for this probability density curve is now very, very different to another probability density curve, even though the mean has not changed. So all these curves have the same mean to or mean time between failure. The balance point has not changed, but the L10 or the B10 life has. And that's the sort of thing we're interested in when it comes to understanding preventive maintenance intervals or warranty periods and everything else like that. And so the mean time to failure or mean time between failure doesn't contain a lot of useful information when it comes to that sort of stuff. So the mean time to failure, you can clearly see, is not a failure-free period. A lot of people think it is. A lot of people think mean time to failure equals failure-free period, but hopefully you've just seen that is not the case. Remember, about 50 to 80% of things fail before the mean time to failure. And so that dispels the next myth that, well, some people think the mean time to failure is close to a largely failure-free period. Well, nope, it's not even a little bit. If you're interested in a failure-free period, you need to look at the B10 life, the L10 life, or the L5 life, or whatever it is that you define as a largely failure-free period. And that means you're talking about reliability and not the mean time to or between failure. So mean time to or between failure is not a reliability metric. And reliability engineering is always about the vital few, not the trivial thousands. And so what that means is that, as I said, you're largely interested in knowing when the L5, B10, L10 life of something is to make important decisions about warranty periods, service lives, preventive maintenance, or bearing selection, so that that bearing is highly unlikely to fail in the life of your vehicle or whatever application it is. So the mean time to failure can't help you with that, but that also should reinforce the fact that we're interested in that first small fraction of things failing, which again brings us back to reliability, the probability of something failing at a designated period in specified conditions. You might be interested in the probability itself or the designated period, but it's all down to reliability with that reliability curve. And the last key message is that just because something is random doesn't mean it's unpredictable. So on that note, are there any questions regarding what is reliability, everything we talked about? And if there's not, we'll come back to Yeshwanth's question about regression models. Also give me a chance to get some fluid into my face. Any questions or comments? All right. Not a lot of coming through yet, or they're so massive that people are taking half an hour to type. So Yeshwanth asked, are regression models a valid technique to predict reliability? What would be a drawback to using them? So regression models are essentially, they're well defined in terms of what they are in the statistical world, but essentially a regression model means that we take data, like the times to failure of a ball bearing, and try and find a model that fits that data. That could be the probability density curve that we think fits the time to failure of a ball bearing. Now, if you have, let's just say we have 1,000 times to failure for ball bearings, that's not unusual actually, especially in certain testing scenarios. You might be able to fit, using a regression model, perhaps a Y-ball distribution or a log normal distribution to the way your ball bearings fail. That model, that log normal model, that Y-ball distribution, whatever it is, then can be very useful when it comes to predicting when, for example, 5% of ball bearings in the field might fail. Very, very useful. When we talk about predicting reliability, however, just want to be clear, there is predicting reliability and then there is predicting reliability. Reliability prediction, a lot of engineers will tell you that's where you go to a guidebook or a handbook, usually on the web, and say, well, I want to know the failure rate of my developmental two-stroke engine. So I'll go on the internet where there are books and tables which say, well, here's a typical failure rate for a two-stroke cylinder engine. You say, okay, that's going to be the failure rate of my two-stroke cylinder engine. That's what people think reliability prediction is. And it's not, because it's a failure rate. And I haven't got time to explain why that's not cool. But if you're talking about reliability prediction in a very true sense, in that you've got times to failure of 1,000 ball bearings, therefore you should be able to predict the reliability of those ball bearings at 2 years if you know the usage rate. Absolutely, you can do that. And there's lots of other webinars I've done which sort of talk to that as well. Rival analysis is one way of doing that. So hopefully that answers your question. Now, I cannot see any more questions coming up. I've done it, Fred. Been able to a webinar where I've answered every hypothetical question as I've gone through.
All right. Well, I got one question for you.
Let's go for it.
Well, a lot of people we work with don't think of reliability as a probability at all. They think it is that it just works. It's trustworthy.
Yep.
So how do you deal with that?
Well, it's the same as safe, isn't it? I mean, people say, well, what's safe? We often use the term safe to describe something where we believe nothing bad will happen. But in practice, safe is a scenario where the probability of something bad happening is acceptably low. And so when people say, okay, will it work? Will this ball bearing last the service life of our vehicle? Which is not an unreasonable question. In practice, whether we like it or not, when we talk about something lasting, we're just saying the probability of failure is acceptably low for me to say, yes, this product will last the duration, the service life, the warranty period, whatever it is. And that's as far as we can go. So the answer might be a straight yes, this will last if there's a shared understanding of what lasting means in that very probabilistic sense. Or if you're a reliability engineer who's being asked that question and you know the person asking the question doesn't get that, you might need to educate as you go. You say, look, yes, it will last in that we believe there is a less than 1 in 100 chance of this thing failing during service life. So we'd expect no more than 1% of our things failing during the service life of our product. Hopefully that will head them off at the pass, so to speak. Did I come close, Fred?
Yeah. Yeah. No, it's a lot of people don't think like we do about reliability. We use that 4-part definition. And so when somebody's trying to set a goal, they'll say, oh, it's a 5-year goal. Right? Well,
yeah.
What balance point do you want here?
Right. And if someone says, well, will it last 5 years? And you say, yes, it will, because the mean time to failure is 5 years. Well, we now know that that's wrong, because if the mean time to failure is 5 years, that means that anywhere between 50 to 80% of your products will fail by that 5-year mark. And that definitely isn't an acceptable definition of last. We've got a question. Dan writes, sometimes people in my company try to lift the reliability reports to the level of a V&V protocol with acceptance criteria, go, no-go threshold. That's more of a comment. And I would not philosophically have a problem with that. The problem with go, no-go criteria is that often people want a level of certainty or imply a level of certainty, which you just can't get. So for example, I was working with a client, it's a developmental product. They wanted go, no-go criteria for, should we use this different technology for our products? And the answer was, it's a hell yes, it's a go. Qualify with the fact that you need to do these things to make sure this is embedded in your product. We know that about half of all failures tend to occur at the interfaces of components and systems. So you just can't get a new technology, put it into your product without thinking about how it interfaces with the other components and expect to have reliability remain the same or even improve. So go criteria, when I give that go criteria, I say it's not just an assessment of the technology, it's an assessment of your organization, because it could be go in another organization which takes that sort of stuff seriously. So, for example, you might do an interface for MIA, or the other organization says, I want an assessment on go, no-go criteria. We intend to have an interface for MIA. We intend to do this. We think it's going to, if it does fail, it'll fail like this, and we want to work on these things. But beyond that, can you tell us, is it go/no-go? And their attitude towards incorporating new technology is part of my assessment about it being go, no-go. If a company says, I want a go, no-go summary or assessment based on this component, and they clearly don't intend to do anything to make sure that component, that new technology gets embedded in their product in a meaningful way, it's always no-go, because if you're not interested, you're not interested. So hopefully that sort of elaborates on your comment down a little bit. But yeah, so the go, no-go is always about what we're going to do to make it work. Any more comments or questions? Thank you, Carl. Now, as you guys, as you veterans know, that if there are questions, I hang around and answer them as best as I can, but I will note that we're about 1 minute out of the allotted time, and I'm not being, thank you, Commandra. No worries, each one. I'm guessing I answered the question, or well enough. Thank you, Chris, mate. Much appreciated. Great name. I think the sharp stabbing pains from these stitches, I was able to suppress my facial expressions well enough for it to not be off-putting. Thanks, Julia. And last call for questions or comments before we call it a day. Thank you very much, Shishir and Julie. Carl's got a question. What are the factors that affect reliability and validity? That's like, it's not quite as up there with, is there a guide level, but it's getting there, because so many factors affect reliability. And when you say validity, that's not a term I'm super familiar with in the world of reliability and quality. I know there's data validation and things like that, but I don't think we've got enough time to answer that question. That's a 17-part seminar in terms of the factors that affect reliability, and I'd need a bit more background with validity. We do know, like for our ball bearing, for example, it's not just how quickly things wear out, it's manufacturing defects, manufacturing quality. It's how, if you look at those different factors, that random hand failure, we know particle contamination drives the majority of ball bearing failures. Particles will get into your ball bearing eventually, but if we can control the environment well enough, you can extend the reliability or extend the useful life of so many ball bearings and other products. So there's so many factors, and it comes down to you understanding the failure mechanisms, the dominant failure mechanisms for your device, which then will let you know what you can do to slow them down, or perhaps even remove them entirely. Any more comments or questions? I think we're close to there, Fred. All right, so let's share the link, which I won't open just yet, but looks marketing factors affecting reliability of tests. That is a different topic, and maybe a whole webinar might have to be devoted to that. For those of you who either too shy to ask a question or are like me, you ask questions or remember things to be put on the grocery list after we go and buy groceries, feel free to reach out. You've got my contact details through Ashendo. More than happy to discuss pertinent reliability engineering challenges moving forward.